Hey, nice to meet you. Seems like a really crowded room. So I'm going to basically talk about a little different thing. We probably might be actually hearing people talking about algorithms and applications. So as these deep learning applications become really prevalent, one of the major challenges you're going to have is how do you compute them faster? And there's actually a huge trend where, of course, people have been using CPUs for a long time, but then the last few years, we've been using GPUs. So pretty much if you're doing, let's say machine learning and deep learning, especially, you use GPUs, beyond gaming cards. And there are other things beyond GPUs that are actually, evolving. I mean, for example, yesterday, Google released the chip, the Tensor chip, which is essentially a chip for doing TensorFlow. So you're going to see a lot of those things. I'm just going to give you like an overview of all these different things that are happening, and what are some of the challenges in accessing each of them, and what's the best way to access them. So as you said, I run a company called Bitfusion. We have offices here, and we also have offices in Austin. So actually what we do is, as these new kinds of architectures actually come in a data center, like for example, your cell phone basically has like so many different architectures. It's got a GPU, it's got a speech processor, it's got like a Wi-Fi chip, everything. The same thing is happening in a data center. You have like a bunch of different pizza boxes with different types of components. As this happens, the biggest challenge is how do you access them? So essentially what we do is we basically build software that allows you to combine all these different things across multiple servers and create one mega server, a virtual server. So in some ways we kind of do what people have been doing in software-defined storage, where you can pool storage. We do the same thing for compute, but pool different kinds of compute, like CPUs, GPUs, FPGAs, DSPs. New architectures come in. We basically have a platform that allows you to pool them in an interesting way. So that's what we do, but to get into the fundamental problem, if you see the fundamental problem in computing, the graph kind of looks like this. So on one side, you have software. It's actually very abstract. As software developers actually build just software, they just want to think about algorithms and applications, don't want to worry about hardware. It's just becoming like use case driven. And then on the other side, there's hardware, which is becoming complex and like really fast, right? So for example, you have CPUs, which are basically hitting the limits of Moore's law. GPUs, they're becoming better and better. At GTC, the NVIDIA essentially announced that they're basically putting a new chip with like 150 billion transistors. There's new chips that are coming up, like like Google's TensorFlow chip. There are FPGAs, there are DSPs. There's Nirvana, which is actually a company in San Diego, which is basically building a chip which basically runs a deep learning framework called Neon. So there's a big gap, So the fundamental problem is, as software becomes abstract and hardware is becoming complex, there's a huge gap. And at the end of the day, why is software becoming? Why is there a problem? It's a problem because application delivering performance is the only thing that matters to applications. So to put things in context, the software world is increasingly abstract, right? As you can see, new GitHub repositories, there are so many different programming languages that are coming up. And if you look at like let's say the job trends, if you look at machine learning, of course the job trends are like growing up, in GitHub. On the other hand, transistor scaling is ending. Essentially, Intel basically was saying, hey, 18 months is what Moore's law is. I'm going to basically build new chips, but now it's 2.5 years. And it might actually become even worse because as the process becomes smaller and smaller, it's challenging. And you can kind of see, that happening over the last 2-3 years, and it's going to become even more prevalent. And as I said, it's 2.5 years more than 2 years, these days. So this is kind of how the background looks like, right? So during the era of frequency, you had Intel, IBM, and AMD building chips faster and faster chips. Frequency, frequency, frequency. Then they said, okay, multi-core. Let's actually build more cores and actually do things more in parallel. That's when MPP and everything came. Again, the same big guys, Intel, AMD, Intel. Then the era of mini-core came. They say, okay, multi-core is interesting, but let's actually put more cores and actually make it more distributed. Again, the same big guys. Then you started building special cores, right? Which is where, obviously, in the mobile, world, you already have actually, guys like Qualcomm doing it. But then you even had, other people, like for example, you have network processors, like the Tyleras of the world, who basically said, I'm going to build network processors for, doing, network chips. Again, the same guys and a few other guys like Qualcomm, and then ARM came in and said, hey, okay, now I can actually do things. Why do you need just Intel and IBM? Why do you just need Power and x86? Hey, you can actually have this ARM thing. Everybody can license this ARM. That's what every cell phone has. Most of the cell phones, none of the cell phones have Intel today. It's all ARM. And Qualcomm is essentially a consumer of ARM. They're basically building, both, chips for, compute as well as for, DSPs as well as for telecommunications. Then Easy Chip, they're basically building like, network processors and so on. Now, if you look at the world today, that's how the world looks like today. You have NVIDIA, and of course, NVIDIA is, when I say now, the last 10, 15 years, right? So NVIDIA, there's, Google, which is a new player. Software companies are basically starting to build chips because they say, hey, look, I have this problem, so I'm going to basically build chips to solve my own problem. There's MediaTek, and even we might see cloud service providers actually building their own chips. There's Xilinx, Altera. There are companies all over the world. Companies in Asia, companies in Europe actually building chips to do what they want. So if I basically have a problem, I'm going to just build the hardware to do this thing. So still, there's one particular problem that exists. The first graph that I showed you, where software is becoming abstract and hardware is becoming complex, the gap that is actually not filled, it still exists because now you have all these different things. So Google is going to build a chip to just do their thing. Amazon is going to build a chip to do only their thing. So what happened to all these all of us, like all developers, building like startups, mid-market companies who cannot go and build a chip? How do I access all of these things? So that is one of the first fundamental problems that still exists. Now there's some I kind of led to this thing a little bit, right? Developers are the guys who actually make everything happen, right? Again, there's a specialized hardware, low hourly pricing, as the libraries, APIs, and everything. How are you going to access it? So the remainder of the talk is primarily going to be about in details about the hardware that's out there and how to develop for them. So there's all these hardware. How do you develop for them? So the reason this is important is the current state of developer experience for anything other than a CPU is challenging, right? For example, if it's a CPU, I can run it on my laptop. But if it's anything beyond a CPU, it's not easy. If it's, I'd say, even for a GPU, installing drivers is sometimes is a pain in the butt. If you start looking at DSPs and FPGAs, it's again even more pain in the butt. I was actually talking to a guy who actually builds the compilers for the Qualcomm chip. The Hexagon chip, and I was talking to a bunch of people, and they were telling me that, hey, I asked them, have you guys ever developed as a user on your chip? They said no. So they don't even own that chip. They basically write compilers for it at work, but they don't own the chip because it's really complicated to develop, right? So, this is very known, right? GPUs, we all know this, right? If anybody has done development with GPUs, the Stack Overflow, all the problems that people put on Stack Overflow. So the first set of, simple, things are integrated GPUs. Essentially, that's something that sits on everybody's laptop. Intel laptops, every laptop basically has this. And essentially, it's essentially a SIMD, architecture that they have, which is basically single instruction, multiple data kind of architecture, which is very shared resource. And primarily, the workloads that are targeted are, workloads that are not really compute intensive, but are latency sensitive and cost sensitive. For example, media, encoding, media transcoding, and things like that. And the programming models that are there is basically OpenCL. OpenCL, if you guys actually, OpenCL is basically another, parallel programming paradigm like CUDA, and support direct compute. Suppose C++ as well, because Intel actually built it. They want to make sure things actually work with the C++ level. Then you have SPIR, HSAL, and all those things. The ecosystem maturity for this is very high because everybody has this on their laptop. Now anybody can develop it. So that's the state of integrated GPU. And the way actually things actually work is essentially it's on the same chip. So if you basically have 4 cores on a CPU, the 4th core is essentially integrated GPU. So this is basically the most common thing that's out there. The next one is discrete GPUs, right? Which is what the NVIDIA cards or the AMD cards that are out there. Essentially, they are essentially PCI cards that you essentially put in your PCI. They either come in essentially like Gen 3x16, and things are actually going to become even faster. They are not a first-class citizen. They are still a second-class citizen because it still has to go through the CPU to do any kind of work. You need a CPU. It doesn't run an operating system or anything. Again, same SIMD, but you can put larger workloads because it's much bigger and it's not small. And it's much more, it's not latency sensitive. It's very throughput sensitive because it has this thing that has to go through the CPU to do certain things. It has to go through PCI, and that PCI is basically 60 gigabytes per second, right? And you have the programming models, OpenCL, of course. AMD supports OpenCL, and even Intel has actually discrete cards like VCAs, which are visual computing accelerators. And of course, the most popular one is NVIDIA's. And NVIDIA basically built this thing called CUDA, which is essentially their programming paradigm. And they built it in like about 7 to 10 years ago. And that's now really becoming popular. And one of the reasons I think that became really popular is because people started building a lot of libraries. And they said, OK, there's all these things out there, just like the web, right? If I want to build a website, I essentially have libraries. I can build stuff for my website. Again, the maturity is pretty high for this. And very good for matrix computations. Then you have mix. This is essentially what Intel calls it Xeon Phi. So it's actually a class of processors that Intel builds. Right now, the version is called Knight's Landing, which is not public. It's kind of public in universities and labs, but it's not public to everybody to use. The most public version is Knight's Corner, which is if you basically Google Xeon Phi, you can essentially buy something for $200. It's again a PCI card, extremely power hungry, large size workloads, high throughput, but primarily for HPC. People doing computational fluid dynamics, all these guys are using it. And Intel is now actually targeting this even for machine learning and deep learning as well. So if you guys basically and I'm assuming this presentation will probably be up online. If you actually go through the link, you can actually find some examples on how actually they'll be using it for machine learning and such. Again, supports OpenCL, supports OpenMP. It doesn't support CUDA. It supports MPI, and it also supports C++, in some ways. So again, ecosystem maturity is actually pretty high in the HPC world, but it's not very high in the deep learning or the machine learning world yet. And I think this might change as Intel releases the Knight's Landing, which is actually going to be the next version. That it's kind of public, but it's not widespread. When that actually happens, I think this is going to be become very widespread. And once it becomes integrated into the first class citizen, as it becomes a socket, because Knight's Landing is essentially going to be a socket. You don't need to be a PCI card anymore. It will become very, very popular. It's going to be very interesting to watch in the next few years. Then the interesting boy comes here, FPGAs. I mean, FPGAs are nothing but field programmable gate arrays. So essentially, it's kind of like it's a big switch with a bunch of programming logic, and I can wire it to do however I want. For one moment, it becomes a speech processing chip. Another moment, it can be a image processing chip. Another moment, it can be a visual processing chip. So again, it's essentially a bunch of LUTs, logical units, with a very tight fabric that it's connected with. So essentially, it's kind of like a big multiplexer in the front, and you have a bunch of logic gates, in between, or logic units in the before that. Again, it's used as co-processors. Again, it's a PCI card. The problem here is right now it supports OpenCL just recently in the last 2-3 years. But the problem is, so far it's been supporting only VHDL and Verilog, which no software guy understands. So what they've been doing is people have been building IPs and libraries on top of it, and people have been actually sharing this with everybody. Then you have things like Automata, which is again the next guy in this mix. This is actually a chip, very interesting chip. This is a chip actually that's actually done by Micron. Their vision for doing this is they want to essentially say, hey, what is the best place to do compute? You want to get closer to the data. So what they actually want to do is they want to basically put compute next to the memory. Micron is known for making DIMMs, memory DIMMs. So what they basically are trying to do is essentially build this and put it as a part of the DIMM. So now essentially you actually load things up in memory and you can essentially do computation. And they are targeting very special purpose things. And these are actually subtrees that came out of things like FPGAs. So you essentially can actually, it's an NFA. If you guys, it's an automata. If you guys actually understand, you guys, computer science, data structure classes, right? It's an NFA on a chip, essentially. It's a programmable fabric. It's again, it's like multiple inputs on single data stream, and it's all pattern matching, essentially. It's completely pattern matching. They're very good for things like bioinformatics, very good for regular expressions. So for example, if you're doing a SNOT, and if you're doing, let's say, DNS detection and things like that, this is actually very good. And since it's regular expression, it can actually be applied for machine learning as well. Because if you look at machine learning, not the deep learning side of things, but the old school machine learning where you're just trying to do pattern matching, this could actually be a very, very interesting thing. And this could actually work in a lot of low power scenarios. Again, the ecosystem maturity is at its infancy right now. You can actually go to Automata, micronautomata.com, and they actually have an SDK and they have a whole simulator and everything. You can actually play with it. In fact, this is actually available for access at University of Virginia. So you can probably request access, and you can probably play with it if you guys want to. And if you guys anybody wants to play with it, let me know. We work with these guys, and I can probably help to get you guys access on this as well. Again, it's, as I said, right, it's very, very low. They're basically building APIs. They're in the infancy where NVIDIA was, probably 10, 15 years ago. Then comes application-specific processors. So just like how Automata said, I'm going to do this for a particular stream, application processor like, hey, I need molecular simulations, I'm going to build a chip for that. I need deep neural networks, I'm going to build a chip for that, which is what Google built, right? I need a thing to do speech processing. I know like 15 other companies that are basically building a chip specifically due to speech processing, right? Because for speech processing, it's basically a bunch of RNNs, and the network is actually a bunch of small networks, but a lot of them dispersed. So the ecosystem maturity is hardly any, right? Only big companies with big budgets essentially actually do this thing. Then, Google's, yesterday's release, right? Essentially a TensorFlow chip. So, which is essentially powered for deep learning. They already been applying it for, the rank brain to improve the search relevancy, and also in the street view to essentially improve the, map accuracy. And in fact, the AlphaGo game was actually powered by TPUs. So this is actually the data center. So if you actually have been using Google's actually API for the speech recognition, you've actually been using this chip. You just didn't know it. It's become so abstract. And then, the more interesting thing is quantum computers. Architecture, it could be varied, right? Targeted workloads, it basically solves an optimization problem, which I think is going to probably happen in the next 10 years. There are some really interesting startups doing it. There's Rigetti Computing, which is actually doing quantum computers. Of course, D-Wave is actually doing quantum computers. IBM just opened up their quantum computer access to everybody. So you can probably go and get access to it. And programming model, nobody knows what the programming model is. Ecosystem maturity, nobody has a clue. But this actually is going to be very popular in the next few years. Still, the accessing this is still a problem, right? So the point I was actually trying to make here is there's, so as these different types of architectures are getting out in this space, once you actually make it accessible and make it available to normal people, when I say normals, like developers, magic could happen. So and our company essentially what we actually do is we try to actually solve this problem. So if you basically essentially how do you actually access like FPGAs, how do you access DSPs, how do you access GPUs, all from your laptop, so you don't even have to actually go to the cloud. So that's essentially what we actually do. Hope this is useful. You can follow me on Twitter, Subbu Rama, or you can follow Bitfusion.io. Happy to answer any questions.